So I am looking at page 123, and I want to start to define calorimetry problems. And just a word of warning, I think that these calorimetry problems are probably the most challenging type of problem that you're going to encounter in College Chemistry 1. So I'm going to break it down for you as much as possible, and I've divided these calorimetry problems into different types, and I'll go through the types for you in the next video. But let me give you an introduction to how you want to approach these problems in general. So remember that the big assumption that we make when we're doing calorimetry is we assume that our calorimeter is an isolated system. So the big assumption that we make whenever we're doing these measurements and whenever we're solving these types of calorimetry problem is that we assume that the calorimeter is an isolated system, which means that no heat is leaving your calorimeter or entering from the surroundings into your calorimeter. So the way I can write that same idea in an equation is that I'm going to say that the Q of my system, that's my calorimeter, is equal to 0. And what this equation means is that there's no changes happening between the system and the surroundings. No heat is leaving my calorimeter, so there's no heat exchange with the surroundings. So this equation here is telling me that no heat enters or leaves the system, which is my calorimeter. If I take this Q system, I'm going to break it down. So I'm considering what's going on inside my calorimeter, and I want to look at the heat changes within my system, within my calorimeter. So I'm going to take this Q system, and I'm going to break it into two terms. And the two terms that I'm using are Q gained, and this represents whatever in the system is gaining heat. And I'm going to add that with Q lost, and this is whatever in the system is losing heat. So I'm looking at the heat transfers that are happening within my calorimeter. And I'm going to set those equal to 0 because I know that no heat escapes the calorimeter. So whatever's gaining heat in the calorimeter is directly gaining that heat from whatever's losing heat within the calorimeter. So the net change is going to be 0 within my system because all of the heat is being contained within my system. I'm going to rearrange this equation a little bit. So I've got this equation that Q gained plus Q lost is equal to 0. I'm going to subtract Q gained from either side. So I'm going to subtract Q gained from this side. Oops. And subtract Q gained from this side. And what I end up with is I can say that Q lost inside my calorimeter is equal to negative Q gained. And this equation here, this Q lost is equal to negative Q gained, is a really useful starting point for your calorimetry problems. So I just wanted to show you where I got this from. And I got this equation here, this Q lost equals negative Q gained. This is coming from my big assumption, which is that my calorimeter is an isolated system. Because no heat is leaving the system, I know that whatever loses heat within my system, within my calorimeter, has to be equal to whatever heat is being gained by substances within my system. And then I've got to keep track of those signs for my heat transfer. So that's where that negative sign comes in with the negative Q gained. So this equation right here is a useful starting point. For your calorimetry problems. So I'm going to stop this video here, and where we're headed to is I'm going to show you different types of calorimetry problems that you're going to see and show you how do you go about defining and solving those problems. So I'm going to stop this video here.